In my second example, I have an isosceles triangle. I'm told that the perimeter is 32 inches. I'm told that the altitude of that isosceles triangle is 8 inches, and I'm asked to find the length of the legs that would make the perimeter work out to be that length. Same kind of thing as I've done in a lot of these problems. Notice that I have right triangles here. If I can get all 3 legs of the right triangle labeled with something, I'm going to be able to get a representation to put into the Pythagorean theorem, and I can come up with a solution. So a few things here. First of all, I'm going to label the sides x and x. Box these in. I'm going to label the sides both with an x. 32 is the total perimeter. I've just used 2 x's. Okay, so what I have left here is 32 minus 2x. That's the remaining part down here. And again, notice if I add 32 minus 2x and x, the x's cancel, and I get a perimeter of 32. So you can always check and make sure you labeled this right. This is broken into 2 equal parts. This is an isosceles triangle. We'll break into 2 congruent triangles. So 16 minus x is this length here. And again, you'll notice at this point, I have 3 sides of a right triangle labeled with the same variable. And I should just be able to put everything into the Pythagorean theorem and come up with a solution here. So Pythagorean theorem says that the leg squared, okay, in this case that's leg squared is 8 plus the leg squared, which is 16 minus x squared, is equal to hypotenuse squared. And again, I can simplify here. Be careful as you go through here. That is a FOIL problem, okay? That is technically the quantity 16 minus x times the quantity 16 minus x. You do need to use FOIL there. 16 times 16 is 256, so this is going to be 64 plus, it'll be 256. I'll get a minus 16x minus another 16x is minus 32x, plus an x squared is equal to x squared. I'm kind of cramming that in a little bit, but you can see there. Something fantastic happens. I have an x squared on this side of the equation, and I have an x squared on the other side of the equation. So I can subtract x squared from both sides. The x squareds cancel. Move my equation over here a little bit. I get 0 is equal to, and I have all this stuff over here. Okay, 64 plus 256 adds up to 320. So I have 320 minus 32x. I think I like these numbers here. Equals 0. I can add 32x to both sides here. And I'm going to find out that 320 is equal to 32x. What does it tell me? It tells me that x is going to be 10. And if you go back here and you look at the original problem, if x is 10, 16 minus 10 would make this side length 6. Notice these are little 6, 8, 10 right triangles. Okay, 10 plus 10 plus 12 for that whole side does in fact add up to 32, and the side lengths work in the Pythagorean theorem, so I know I have a correct answer. In this problem, I'm told that I have the diagonals of a rhombus, and they form a 2-to-1 ratio. Their lengths are in a 2-to-1 ratio. I'm also told that the perimeter of the rhombus is 20 centimeters. What I'd like to find is what those diagonal lengths have to be in order to create a rhombus that meets the specifications listed in this problem. Number one, always a good idea to have a diagram. Remember that a rhombus has 4 congruent sides. A rhombus is a special kind of kite with 4 congruent sides, meaning that the diagonals are perpendicular bisectors of each other. And that's going to be very crucial here. So perpendicular bisectors. I've got right angles. These things are congruent to each other, and these 2 things are also congruent to each other. And more importantly, I have a lot of right angles. The perimeter is 20 centimeters. So if it's got 4 equal sides, 20 divided by 4 tells me that each side length is 5 centimeters. And it says that the diagonals are in a 2-to-1 ratio. So basically, 2 parts goes with one diagonal, 1 part goes with another. I could do like a 2x with this entire diagonal and a 1x going this way. I'm actually going to expand that to a 4-to-2 ratio and have a 4x and a 2x. And what that allows me to do is to create a smaller diagonal here, call this length 2x and that length x. And the reason I'm doing that, it still results in a 2-to-1 ratio for the whole lengths, because I get a 4x to 2x It simplifies down to a 2-to-1 ratio. But more importantly, it lets me label two sides of this right triangle. And again, if I can get if I can get all three sides of a right triangle labeled using the same variables, very easy to write an equation using the Pythagorean theorem. So the Pythagorean theorem says that the leg squared plus another leg squared is equal to a hypotenuse squared. And if I go ahead and simplify this a little bit, I get 4x squared for the second part. And I find out that 5x squared is equal to 25. I can divide both sides by 5. I find out that x squared is equal to 5, meaning that if I take the square root, and again, I'm only interested in the positive square root here since this is the length, x is equal to radical 5. So my final diagonals here, this length here is going to be radical 5, this length over here is going to be 2 radical 5, and if I'm looking for the lengths of the full diagonals, I can double that. One diagonal is going to be 2 radical 5, and the second diagonal going the other way is going to be 2 radical 5s, which is 4 radical 5. Those are my two diagonal lengths that meet the requirements of this problem.